Okay. Last week we talked about alkenes. Those are single bonded carbon-carbon only. Today we're going to talk about alkenes and the aromatic compound. Those compounds have something called a double bond and a single bond combination. At least one double bond, but now more than one double bond. Now, this is an allied health class. Allied means health. Okay? We're not studying any chemicals that are not natively in our bodies. Okay? And that is triple bonded carbons and nitrogens. Those don't exist in our bodies. And also polymers, commercial polymers. No, I'm not studying those in this chapter either. We're going to study biological polymers when we get to it, like proteins and carbohydrates, for example. We're not studying things like PVC or anything like that. Okay? Now, when we're naming stuff, normally we put things in alphabetical order. Mono, dot, pi, tetra doesn't count. It's the main molecule, main noun that determines the alphabetical order, except for iso. You know, isopropyl, that begins with an I. Propyl begins with a P. Dipropyl begins with a P. Tripropyl begins with a P. Okay? So the only one that doesn't count is iso, and that's considered an I. Okay, so let's talk about first naming. Now, as you know, every test is going to have naming on it. Name to structure, structure to name. Every test is going to have intermolecular forces. Every test is going to have reactions. No exceptions, except for the very last test. That's going to only have biochemical reactions. Okay, so how do you name these? Well, just like before, first step is to identify the backbone. Okay, in this case, you've got a 4-carbon backbone with no branching. So the way this goes is you always have to name it 2 ways. In this case, it doesn't matter which way you go, left to right, right to left. Get the same numbering. So this is going to be, where does a double bond start when we're going from left to right? On carbon number 2. That's why we have to name it with the 2 there. So it's really from carbons number 2 to 3, but it starts on carbon 2. Okay, and the functional group is a double bond, which is Ene, E-N-E. So there's alkanes, alkenes. Okay, that's probably the simplest one. Now, double bonds are rigid. Now, remember, last week I said that whenever there's rigidity possibilities, then we could have cis-trans isomers. So as soon as you see a double bond, you go to the double bond and you look at it. Now, on this double bond, there's an H coming off here, there's an H coming off there, and there's no methyl groups or any other group coming off there. So there's no cis-trans. There's only hydrogens coming off, no cis-trans. Okay, so let's look at another one here. This guy here. Again, step 1, backbone. Okay, we've got, and the backbone, now this has got no exception. The backbone has to include the functional group. Functional group is a double bond. So the backbone has to include that. No exceptions. So we couldn't go like this. That would not work because it doesn't include the double bond. So we can either do this or this. Both of them are valid backbones. Either one has a branch. Let's choose the yellow one. Okay, so we have to number. Now, the functional group numbering lowers. The lowest functional group numbering wins out. So in this case, we're going to start on the left. If we start on the right, it's going to be a high number. So that means that's 1, 2, 3. Oops. 1, 2, 3, 4. So 4 is buta. And it's a double bond, so it's ENE. Okay, we've got a branch at carbon number 3, so that's 3-methyl. And where's the double bond? The double bond starts on carbon number 1. So that's 3-methyl, 1-butene. All right. Always 3 parts. The branching is optional. Okay, let's look at this guy here. The yellow backbone. If we tried to do another backbone, it would be 5 carbons long. The other backbone, 6 carbons long. So the yellow one is longer. So we're going to use the yellow one. Okay, 6 carbons long. That means it's a hexa. And it's a double bond, so it's an ene. And we've got a branch at carbon number 4. So it's going to be 4-methyl. And double bond is on carbon 2 to 3. So that's 4-methyl 2-hexene. Now, you can have multiple double bonds and you can have cyclic double bonds. Multiple double bonds is going to be labeled with a di for 2, diene. Backbone. We've got 2 branches, 2 methyl branches, and 2 double bonds. So it's going to be, one is going to be a buta, and it's going to be 2 double bonds. So we have to say diene. And what are those double bonds located? On carbons 1 and 3. And then we have 2 methyl groups at carbons 2 and 3. So it's 2,3 dimethyl 1,3 butadiene.
Could you explain the naming on that one more time?
Say again,
Could you explain the naming on that river line, on that example?
the one we just did?
Yes.
Okay, so just ignore the name for a second. Just looking at that. One, on the backbone, we've got two double bonds.
Mhm.
Okay. That's reflected here.
Okay.
Okay, and where are they located? Carbon 1 and 3.
Mhm.
So we're going into the double bond
Mhm.
as we count. And we have two carbons that are off the backbone. Two methyl. Carbons 2 and 3.
Okay. That makes sense.
All right, now we can also have cycloenes, just like we can have cycloalkanes. Oh, by the way, are there any cis or trans on Earth? Okay. What you need to do to analyze that is to look at the double bond. Okay, this double bond has got a two hydrogens. Because the hydrogens are the same on both sides, it really both cis and trans together. So that means it's immutable. So there's no cis or trans in this molecule. Same on the right side. Okay, so let's look at the cyclic nature now. Okay, so on a cyclic compound, the functional group normally is carbon number 1. So in this case, the functional group is a double bond. So we can either choose the bottom one or the top right one. Let's choose the top right one. And that means that's going to be carbon number 1. Now, whenever we number with a double bond, we have to number into the double bond. That means the numbering goes this way. If we chose this as number 1, we'd have to go counterclockwise. Again, because we have to go into the double bond. Okay, so we've got okay. Like last week, whenever we have a cyclic compound, that automatically dictates the backbone. So that's automatically the backbone. So let's number this now. Okay, so when we go to number, we're going to start at carbon number 1 and go into the double bond. Into. Okay, so we've got a methyl group at carbon number 2. And then the second double bond is on carbon number 3. So it's going to be going to be 1, 3, cyclo, pentadiene. And we've got a branch at carbon number 2. So 2-methyl 1,3 cyclopentadiene. Now, on TriLab. TriLab is going to be practice on going from a name to a structure. To a name. On the test, you're gonna have the same kind of deal. Name, structure, and then. Now, again, double bonds are rigid, meaning automatically check for cis trans across the double bond. You look at the double bonds here, and we've got the methyl groups falling on either side of that double bond. On the left, the methyl groups are on the same side. On the right, they're opposite. Same side means cis, like sister. Opposite means trans. So whenever you have a double bond or cyclic, always check for the existence of methyl groups in a cis or trans position. Now, cis or trans is a big deal. All of you know about trans fatty acids being bad for you. That's because they're not the natural fatty acids. Fatty acids are cis. So that means fatty acids frequently are used in membranes, separating one area, aqueous area, from another aqueous area. So if your membranes are messed up, your reactions are messed up. That's why the government put a regulation saying either no trans fats or the minimum number of trans fats. Whenever you have heat around fats, always be suspect for trans fats, like deep fat frying. The heat will convert a cis fat to a trans fat. Trans are more stable than cis. Hence, when they're around heat, they'll revert to the more stable configuration, which is trans. As far as physical properties go, it's similar, but not the same. Similar. Chemical property, similar, but not the same. Biochemically, yes, please do. You can always shut that door whenever you don't even ask, just shut it. Okay, so biochemically, it's even more important to pay attention to cis and trans because biochemically, we are very, very, very selective, differentiating between cis versus trans. Very selective. Physical properties. They're almost identical. That alkene. Almost. Very, very close. Chemically, they're more reactive than alkanes. Alkanes are more stable. But as far as the physical properties, are they flammable? Yes. Do they burn? Yes. They smell like gasoline. That's because there's a lot of alkenes in gasoline. They float on water. That means they're less dense than water. Chemically, they're not the same though. They're very reactive compared to alkanes. Only physically. Okay. I'm going to make that distinction, physical versus chemical. Physical means how do they act without anything going on? Similar boiling point, similar melting point. Similar densities. Those are physical characteristics. Now, this is where it differs dramatically from alkene. Dramatically. Now, the reason why it differs dramatically is because alkanes are inherently more stable. Alkenes are unstable compared to alkanes. Hence, they want to react to become more stable. And that's where the tricky part is. Now, alkanes have a single bond, alkenes have a double bond. That means there's two electron pairs in that double bond, but they're not equal. One of them is very stable, the other one is not. The one that's stable is called a sigma bond. And the pi bond is the other one, unstable. So when we react to double bond, it reverts to a single bond. And that revision, it forms a sigma bond. And that sigma bond is very stable. So now this is a trend throughout the rest of the semester. We go from unstable to stable all the time, never the reverse. If we go the reverse, we have to put a lot of energy into the system. Now we're going to find that we can do that. We can go from a nice stable single carbon-carbon bond to a double bond. But we have to put a ton of energy into it. Because the single is so much more stable than the double. It's that pi bond that's the culprit. Now, the first set of reactions we're going to talk about are called addition reactions. Those reactions are when something comes across the double bond, it's added to it. Hence the name addition reactions. What's going to happen is this AB, whatever that is going to go across that double bond. You're going to end up with a new single bond with A and B attached to it. Either one of those carbons. Now, there are four different kinds of addition reactions, depending on what we're adding. Okay, if we start an alkene, and we add H2 to it, we form an alkane. I'm going to give you an example of all these. No mix. That's important. No mix. When we add either, we're not going to use Br2, we're going to use Cl2 exclusively in this class. Okay, so if we add Cl2 across the double bond, it's going to add and become a chloroalkane with no mix. Okay, so these two, no mix. These two have got a mix, and it makes it trickier. When I say mix, that means when we create the products, we create more than one product. If there's no mix, that means we create only one product. Okay, so let's start here. All right, so we've got an alkane. Excuse me, we have an alkene, double bonded carbon. And we're going to add to that a homogeneic bromine molecule. Homo means the same. Hetero means different. So whenever we add a homogeneic addition to a double bond, we get no mix. And the Br, in this case, Br2 could be Cl2. Normally in my class, I like to talk about Cl2 because it's a more naturally occurring halogen as opposed to Br. What happens is each Br adds to each carbon. We end up with Br across each carbon. So let's look at an example here. Now this comes directly from, if you remember on your dry labs I passed out last week, one of them has this on the front of it. You're going to live and breathe with this reaction chart for each unit except for unit 5. These are the reactions you are going to need to know for unit 1. And there are quite a few of them. Some of these we're going to get into on Thursday on alcohol. Talk about oxidation and reduction of alcohol. We talk about the creation of alcohol and a number of types of reactions. Today we're talking about addition reactions. So we're taking an alkene, adding Br or Cl2. Taking alkene, we're going to add H2. Those are the simplest alkene reactions, addition reactions. And those we give no mix. Okay, one reaction as opposed to an addition reaction is it'll burn. We put a spark against that, it'll burn quite nicely, getting that carbon dioxide and water. Now let's look at some examples of those reactions. Let's take that alkene. What is the name of that alkene? Well, it's got 1, 2, 3, 4. So it is a 1-butene. And let's add to it chlorine gas. So number one, you have to name the reactant. In this case, the reactant is 1-butene chlorine gas. What are the conditions? Okay, there aren't any conditions other than adding the Cl2. Okay, next we add the product. What happens when we add Cl2 across that double bond? Now we still have 1, 2, 3, 4. 1, 2, 3, 4. Oops, why did it do that? So the backbone hasn't changed. Now, except for one exception in unit 1, we make ethers. Normally the backbone stays the same. So if our product has 4 carbons, we start with 4 carbons. except for ethers, which is on Thursday. Okay. So what do we end up with? Well, we've got a 4-carbon backbone. So that's a butane. And we've got 2 branches. So that's dichloral. It's on carbon number 1 and 2. 1,2-dichlorobutane is the product. So there are 3 parts to every reaction. We have product, we have reactant, we have to name it, we have to name the conditions to receive full credit. If there's a mix, you have to include the mix as well. Now, with this one, there's no mix, so that's the only product. So that's your first reaction. Now, last Thursday, we had a reaction as well. Remember, we had an alkene plus Cl2 with high heat, and that gives chloroalkane. Now, let's look at the distinction between those two. Here we're adding chlorine across a single bond. And that won't happen unless we add energy. And that energy is heat and light. That's the only way that'll happen. And then our product is going to be 2-chloro butane. Now look at the difference between upper and lower. One, we're adding to an alkane. Notice we have to add energy, because that alkane is pretty stable to start with. When we have an alkene, we don't have to add any energy. That's because it's not very stable. It wants to do something. What it does in the presence of chlorine gas is it adds across the double bond, becomes more stable. So we end up with chlorobutane in both cases. One case we had to add energy, the other case it happened spontaneously. When it happens spontaneously, that means what you're starting with is unstable. Okay, does that make sense? Unstable things want to become more stable, kind of like people. We don't like to go the other way. Same with molecules. They like to go from unstable to stable. It's the natural way to go. Okay, let's look at another example. Let's take okay, what happens here? Okay, we've got a double bonded, we have an alkene around chlorine gas. What happens? What happens? Anyone guess what happens?
Stable.
Hmm?
The double bond turns into just one.
We want to go from unstable double bond to stable single bond, exactly. And we can do that by adding the Cl2 across the double bond. We get a chlorine there, chlorine there. No mix. Now, we've got a name, starting, name, ending. Starting is going to be 1 Okay, 1, 2, 3, 4, 5. 5 carbon backbone. So we've got 2 pentene, no branching. And our product is going to be 2, 3 dichloropentane. Okay, so to receive full credit, we name the reactant, we name the product, we name the condition, we name the correct structure.
When you're speaking on conditions, are you talking about the stability, like whether it's going from stable to unstable or unstable to stable?
No, when I say the conditions, and this, sometimes you have to add heat, sometimes you have to add energy, sometimes you have to add, the catalyst, other conditions.
Oh, okay.
And that's normally conditions are required. Because alkenes are so unstable. That when you buy alkenes, they don't last very long on the shelf. They're not very stable. They have a shelf life. Or alkanes last forever. Unfortunately, in our environment, they last forever because they're so stable. So if it's chlorinated alkane, can used as a pesticide, unfortunately, they're around forever. When I say forever, I'm talking about millennia forever. They don't go away. They're called forever chemicals. Bad stuff for our environment. They're bad for wildlife. They're bad for everything. And we're considered wildlife. Okay. So let's continue on here. That's called halogenation. Cl is a halogen, Br is a halogen. So halogenation, there's 2 ways to halogenate something. One way is this way. Now another simple reaction is called hydrogenation, another addition reaction. This is where we're adding H2 across the double bond. Notice that PT over there, over the arrow, that's platinum. That's called a catalyst. Catalysts speed up reactions. So we can either have no catalyst, slow, or with a catalyst, fast. Get the same results. Now, get no mixture. And basically we form a C-C single bond. We go from an alkene to an alkane. Now this simple reaction is how Crisco shortening. Who knows what Crisco shortening is? Anyone? What is?
I just know it's used for like baking.
And what is it a substitute for? Oil, butter, lard, right? I was raised on Crisco. I'm 75 years old. From the 50s, my mom used to bake all the time. I had fried chicken once a week. I had collard greens and cornbread once a week. I had spaghetti and meatballs once a week. I had roast beef and mashed potatoes and gravy once a week, every single week of my life until I got older. That's when I left high school. My mom used to make apple pies and all kinds of stuff all the time. She's a real homemaker. Well, Crisco is, like she was saying, is used as a substitute for lard. Back in the 50s, it was felt lard was very unhealthy to cook with. Now it's the opposite. My mom, trying to be healthy, used Crisco as a substitute for lard. The problem with Crisco in those days, it had tons of trans fats in it. Because to make Crisco in those days, you took vegetable oil and you hydrogenated. only it wasn't perfect. You didn't hydrogenate all the double bonds, only some of them. The ones that are left over reverted to trans. So Crisco had a ton of trans fats in it. That's probably why my asthma is so bad and all kinds of other health issues. Well, my mom thought she was doing the right thing. Well, Crisco almost went out of business when they started regulating trans fats. So what Crisco did is instead of hydrogenating the double bond, what they did instead was we did a mixture of vegetable oils to give the same consistency as lard. So now Crisco is fine. No trans fats at all. The boy, when I was growing up, was horrible. Horrible. Okay, so that's probably the simplest reaction we're gonna have all day today, is hydrogenation. And H2 across the double bond gives us an alkene. If we wanted to go fast, we're gonna use a catalyst. If we wanted to go slowly, we have no catalyst. Okay, let's see here. Now I'm going to get into a trickier reality when we have a mixture. Now, I keep talking about alkene reactions being unstable. You go from an unstable alkene reaction to a stable reaction. The problem is, if you have a mixture, you have to determine which is more stable between the two or three. Normally it's two. When we make aspirin, for example, 2 or 3 labs from now, we're going to be making aspirin, and it's going to have a mixture. We have to figure out which is the more stable mixture. Okay, there are 2 ways to determine this. One way is to use something called Markovnikov's rule. And here we're counting hydrogens on the end. So if we've got this compound and let's see, we have this compound and okay, so this is 1 butene, 2 butene. Which is more stable? Because you're gonna have to circle the ones more stable. Okay, show of hands. Which is more stable, right or left? Right. Raise your hand. Okay, left. Okay. One on the right is more stable. For 2 reasons. Reason number 1 is symmetry. Nature likes symmetry as opposed to non-symmetrical. Okay, so number 1, the one on the right is more symmetrical than the one on the left. Think of it as more balanced than the one on the left. One on the left is not balanced since it's not symmetrical. Okay? Reason number 1. Reason number 2 has to do with Markovnikov rule. And there you count the hydrogens on the end. The more hydrogens, the more stable. So this has got 3 hydrogens, 2 hydrogens. 3 hydrogens, 3 hydrogens. 6 versus 5, 6 wins. So because of Markovnikov's rule, the more terminal hydrogens, the more stable it is. And symmetry, the one on the right wins out. Hence, the mixture, you would circle that one. Now, if you don't circle the one that's most stable, you'll get deemed point. Now, a synthetic chemist always have issues whenever they make something. The problem is, what is it you want? You want this one or that one? Whatever, whichever one you want, you gotta have purification processes to purify the one you want and pull the one you don't want. Now, this is typically a 60-40 split. 60% the one on the right, 40% the one on the left. So always test it two ways. Sometimes you can't tell, to be really honest with you. And in that situation, it doesn't matter which one you circle. I won't give them credit for either one. But most of the time you can tell pretty straightforwardly which is more stable, which is more symmetrical, which has the most terminal hydrogen. And Markovnikov showed that those are more stable, the more terminal hydrogens. Terminal means the ones on the end. Okay, are there any questions about mixture stability? Okay. Now, this is what's going to happen whenever we have a mix. We're going to have more than one product. Okay, the first one we're going to come to is the addition of a simple acid like hydrochloric acid, HCl. What's going to happen is okay, we've got two butene. I'm going to add HCl across that double bond. We're going to add to that. This is the third addition reaction. What's going to happen is that half the time, HCl is going to be like that. Let's make this more complex. Let's make it two pentene. Okay, so 50% of the time, HCl is going to add H on the left, chlorine on the right. The other 50% of the time, it's going to be opposite. This is why we're going to get a mixture. Half the time it's one way, half the time it's the other way. 50% of the time. So now we're going to get a mixture of chlorine on the right and chlorine on the left. And this, there's an H here and an H here, and that's the original HCl. Does everyone see why we have that mixture? It depends on how the HCl lays across the double bond. 50-50. Now the question is, we have a mixture. Which is more stable? Okay, so we have two rules to go by. Okay, let's get rid of the H for now. Okay, so let's impose our two rules. Symmetry. Which is more symmetrical, left or right? Left. Okay, so symmetry wins there. What about terminal hydrogens? Okay, so how many hydrogens we have here? Three hydrogens on the end. Three hydrogens there. Three hydrogens here. Three hydrogens here. So Markovnikov, who wins there? It's a tie. 6 and 6. So you can't tell from Markovnikov which is more stable. Only through symmetry. And this is why symmetry is important. Markovnikov is okay, but symmetry frequently will help you. Sometimes it's a slam dunk. They're both positive or whatever. But in this case, it's a good example of where Markovnikov failed. Six hydrogens, six hydrogens, terminal hydrogens down. Does everyone see where I got 6? 3 in each end? Okay, so we would circle the left one. And we would also have to name it. We haven't named these yet. So this is going to be so they're both pentane, 5 carbons long. Wait a minute here. Okay, 5 carbons long. In one case, it's going to be 2 chloro pentane. This is going to be 3 chloro pentane.
Right to left and not left to right.
Because if we go from right to left, it becomes 2 chloro. If we go from left to right, it becomes 1, 2, 3, 4 chloro. Lower is better.
Okay.
Is that better?
Yeah.
And the two things, lower the number alkylate. Those are the two things we kind of work back and forth. Okay, so in our reactions here, okay, we've talked about adding chlorine, talked about adding H2, we've talked about adding HCl. Now we're going to add water. I'm going to add water in a sulfuric acid solution across the double bond. Notice when we do that, what do we make? We make an alcohol. Yeah. We're going to see on Thursday how to synthesize alcohol. We start with a double bond. Add water. Boom, becomes an alcohol. So we're going to take 2-pentene and acidic water. What's going to happen is the H and OH on the water is going to add across the double bond twice. So we're going to end up with a mixture. And the OH is going to appear on either side of the double bond. Either side. Now, I'm not going to name these because we're going to name them on Thursday when we get into alcohols. This is basically a pentanol. A pentanol. Okay, so which is more stable? Left or right? Okay, let's look at symmetry. Which wins symmetry-wise? Left or right? Left. Okay. What about Markovnikov? Well, I got 3H, 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 3H. Markovnikov is equal, can't determine it. So the asymmetry, the one on the left, is more stable. Hence, we're going to get more of it. Got to circle that one. So those are the four reactions, four addition reactions of the double bond. We add H2, we add Cl2, we add HCl, and we add water. Four reactions. Okay? Now, what I haven't talked about so far on reactions is, yeah, I gave you reactants and conditions, and I'd say, what do you make? What if I said, how do you make? How do you make? How do you make that? 2-chloro-butane. You're a synthetic chemist. This is what they do every single day. When they make drugs and pesticides, etc. You're shooting for a certain molecule. How do you make it? What has to come together to make that?
Halogenation?
Huh?
Halogenation?
Come together for what?
Or it's halogenation?
Halogenation of what?
Or
Okay, one way, she said halogenation of an alkane. Okay, so we have the same backbone. Backbone is 1, 2, 3, 4. And we need heat energy and Cl2. Remember, that's our alkane reaction. That's one way to make it. But there are multiple ways to make it. Notice we ended with a 4-carbon backbone. We started with a 4-carbon backbone. What else could we do to make that? What are the addition reactions we could use to make that? On a test, I may say, show me 2 ways to make that. Well, that would be one way, starting with an alkane under high energy conditions, chlorine gas. What's another way to make it? What if we go over today? What kind of reactions do we go over? Yeah. Addition across the double bond. Okay. So if we have a double bond, we add HCl, we'll end up with 2-chloro. So those are 2 ways. Actually, there are 3, but there are 2. These are 2 solid ways to do it. We have to name that. That's butane. And this is 2-butene. And this would be 2-chlorobutane. Now, in your dry lab, you're going to practice a lot of reactions. You need to practice it a lot. Now, this is going to be the bane of this class. Everyone says naming is easy. Drawing structures are easy. Intermediate intermolecular forces are easy. Reactions are pain. I've taught this class a whole bunch of times. Up in Washington, I taught it 4 times a year for 12 years. Down here, I teach it twice a year. So far, 4 years. I've taught this class really a lot. Every single class, without exception, because reactions are the hardest. I'm just telling you right out, focus on reactions. They will give you the most trouble. Okay, does everyone see how if I start with 2-butene, I can get 2-chlorobutane? We're adding HCl across that double bond. Sometimes you get a mixture, sometimes you don't. In this case, we theoretically get a mixture, but we end up with the same molecule. Sort of moment. Yeah.
What type of reaction would the second one be?
Addition.
Just an addition reaction? There's no specific name for the HCl.
Well, it's an addition reaction with HCl. So our question was, what's the name of the reaction? It's addition reaction. Using HCl.
First one would be chlorination.
First one? Yeah, or halogenation. Yeah, exactly. The first one would be chlorination. Second one would be addition reaction with HCl.
Would it be considered like hydro, but
Hydrogenation?
to think of the hydrogen, would it be considered that?
No, it wouldn't be hydrogenation because hydrogenation gives you 2 H's.
Oh.
And one of them's got to be a chlorine. It's going to be chlorine, hydrogen. That makes sense?
Mm-hmm.
And built into hydrogenation is hydrogen. Okay, so let's do one more today.
Would it be considered halogenation?
In this case, you could call both of them halogenation. It's just that the route is different.
Mhm.
One is for a single bond, the other is to a double bond. So the second halogenation is through an addition reaction.
Mhm.
The other one is through just flat out throwing energy at it.
Mhm.
I mean, it's the reactions, the main reaction for alkanes is combustion. They burn like a banshee, butane lighters and propane. Oh, it burns really, really well.
Mhm.
Gasoline's another one. Okay, so let's do one more example. And that'll be it for today. Let's do a synthesis problem. Let's make something here. Let's see, have I done any other? Let's see here. Okay, so let's make this alcohol. This is a
Excuse me, Mr. Ferguson.
1, 2, 3, 4, 5. Yeah, but
I noticed you didn't do roll call either today or last week. So are
correct,
we
because
gonna
there's
cover-
no waitlisted people. When I waitlisted people, I have to
No,
take.
no, attendance. You didn't do attendance for this class today or last week? So I would like to know if we got proper credit for those who attended
Yeah.
class
Yeah.
and lab.
I don't take attendance
Okay,
because we're all adults in here. We're not in junior high.
okay,
If you come, as I said, I make videos of every lecture.
right.
So if you miss lecture, you can always catch up on the video.
There's still a disconnect. Is there not any points or anything involved with
Correct.
attendance? So
Correct.
you're not taking attendance? So I want to be clear on that.
Correct, correct.
Okay, thank you.
Yeah, I don't take attendance because we're all adults. Yeah, if
Right,
you
I just
come-
wanted to know how you
Correct.
keep
I
track
understand.
of it for
I understand.
purposes
For
of
clarification.
attendance.
It's just that I feel, I've been doing this for a long time, and if I take attendance when it takes a long time, and it's just, you can sit there and be a bump on a log and get points for attendance. That means nothing as far as understanding the material. That's my reason why I don't take it. I take attendance for the first 2 weeks if there's waitlisted for it. Because the no-shows get bounced, make room for the waitlisted people. Is that reasonable?
Understood.
Okay. All right, so let's make this. Okay, we've got 1, 2, 3, 4, 5. So it's a 5-carbon backbone. And the way we'd name this is 2-pentanol. We're going to go over that on Thursday. This is the alcohol part. So how do we make 2-pentanol? Well, we always start with our backbone on our product is 5 carbons long. What are we going to start with? How many carbons long? Normally it's 5, except for ethers. Ethers I'm going to talk about on Thursday. Normally, if we end with 5, we start with 5. If we start with 5, we end with 5. Okay? Most of the time. There are exceptions. I'll call attention to it when there's an exception. So, okay, so if we're going to end with 5, we got to start with 5. And how do we make an alcohol? So far, I've only taught you one way to make an alcohol. By the way, there are 3 ways to make alcohol. This is one way we learned with it.
So we're adding acidic water.
Across
Alcohol?
on a double bond. Perfect. Okay, so across the double bond, we add water. Now, There's two places we could have a double bond and get alcohol there. We could have a double bond there, or there. Both will give us an alcohol on carbon number 2. Because we're going to add water. There. Or there. So either one of those. We get. Yeah.
This, well, H2SO4 just specific to this, reaction of flavors or capacity.
Yeah, that's part of the conditions. Our question had to do with H2SO4. So this requires water and H2SO4 for both of these. Because we're adding across double bond. And of course, we'd have to name our reactants. So it'd be 1-pentene, 2-pentene. And that is a typical test question. Now, I haven't talked about intermolecular forces. I'm going to talk about them on Thursday in relation to Unit 1 chemicals. Because we've got alkanes, alkenes, alcohol, and ethers. Those are the 4 chemicals for Unit 1. And those vary tremendously in terms of intermolecular forces. So we'll talk about those Thursday. Okay, so that's what I wanted to cover today. Are there any questions about these alkene reactions? Okay. Don't, yeah,
Question about the lab menu. I went to the store and they're sold out for now.
I passed out dry labs 0, 1, 2, and 3.
Okay, so that's what we're gonna be doing this week?
Yeah.
Okay.
I can't, they're out of.
Yeah, yeah.
I go through this every semester. They don't put it on. By the way, if they continue to do that, I'll be applying the digital copy.
Why don't you go over this?
Seriously.